The darkest planet ever discovered reflects almost no light. Astronomers describe it as a world so black it swallows starlight, erasing its outline against the vastness of space. Unlike the glittering bands of Jupiter or the icy white crown of Saturn, this planet hides like a cosmic shadow, more akin to a void than a celestial sphere. It is darker than charcoal, darker than asphalt, and darker than any earthly material the human eye instinctively associates with absence. Its existence is not just an astronomical curiosity, but a psychological disturbance. How can something so massive remain invisible, even as it orbits a star? The discovery forces us to confront the meaning of perception itself. Human vision depends on light, and yet here lies a planet that denies it, a place that consumes illumination rather than offering it back. The concept resonates with experiments in sensory deprivation chambers, where subjects immersed in complete darkness report distortions of time, disorientation, and even hallucinations. Darkness is not merely the absence of light, it reshapes cognition, revealing the brain's dependence on external cues for stability. When astronomers announce a planet darker than coal, they are not only describing a property of matter, but also extending an invitation to explore how the human mind interprets the unknown. The name of this world, Tari S2b, offers little hint of its strangeness. It sits hundreds of light-years away, orbiting quietly around its parent star, yet its blackness defies expectation. Scientists trained to study planetary albedo, the measure of how much light an object reflects, found themselves faced with an outlier so extreme it challenged existing models. For context, Earth reflects about 30% of incoming sunlight. The Moon, with its gray and dusty surface, reflects only about 12%. Yet this planet reflects less than 1%. To gaze upon it would be to look into something that seems not to exist, a celestial paradox. The mind responds to such extremes with unease. In psychology, this is tied to the principle of the cognitive gap, the discomfort that arises when perception fails to reconcile with expectation. Just as illusions exploit the brain's predictive mechanisms, this discovery unsettles because it defies the simple assumption that planets, warmed by stars, should at least glow. Instead, here is a world that hides itself almost completely, daring us to question what else the cosmos might conceal. This bridge between astronomy and psychology is not accidental. The black planet is not simply a physical body, but also a metaphorical construct. Ancient cultures often feared total darkness, embedding it in myth as the realm of demons, chaos, or death. In Norse cosmology, Ginnungagap was a yawning abyss of shadow before creation. In Egyptian belief, the sun-east nightly journey through Duat, the underworld of black rivers and unseen dangers, mirrored the peril of traveling blind. Modern science strips these myths of their gods, but leaves intact the disquiet they describe. A world darker than any night sky brings back the archetypal fear of losing the boundary between presence and void. Astronomers did not stumble upon this discovery by chance. It required the precision of NASA's Kepler mission, a telescope designed to measure minuscule dips in starlight as planets pass before their stars. By analyzing these faint patterns, scientists identified Tari S2b's existence in 2011. But identifying it was only the first step. Understanding why it remained so dark demanded confronting chemical and physical processes beyond familiar models. Each answer gave rise to further questions, deepening the mystery rather than resolving it. In the same way, the human mind seeks closure yet recoils when denied it. Experiments in cognitive psychology show that unresolved patterns demand disproportionate attention. The Zeigarnik effect, first described by Bluma Zeigarnik in 1927, demonstrated that incomplete tasks remain more vivid in memory than completed ones. A planet like Tauri 2b exploits this cognitive bias. It appears as an unsolved riddle, pulling thought toward it precisely because it refuses to give back light. The existence of such darkness in space reminds us that perception is never absolute. What we see depends on interaction, photons bouncing back, receptors firing, the brain assembling fragments into images. Remove that reflection, and the brain is left with absence, which it fills with speculation, illusion, and unease. In this sense, the black planet is not only an astronomical object, but also a psychological mirror, one that reflects nothing, and in doing so, forces us to see our dependence on light, expectation, and meaning. For those compelled by mysteries that blur science with perception, this story is one to follow to its end. Like leave a comment with your thoughts on what true darkness means to you, and subscribe if you want to explore the hidden corners of the universe and the mind. To understand what it means for a planet to be so dark that it disappears into the fabric of space, one must first consider the concept of albedo. In planetary science, albedo refers to the fraction of incident light that an object reflects back into space. It is expressed as a number between 0 and 1, where 0 represents a perfectly black surface that absorbs all incoming light, and 1 represents a perfectly reflective surface that scatters every photon. The Moon, with its weathered basalt and powdery regolith, has an albedo of about 0.12, a fact that surprises many who perceive it as bright in the night sky. Its apparent brilliance comes not from high reflectivity, but from contrast. The human eye adjusts to the surrounding darkness, exaggerating the Moon's dim glow into radiance. By comparison, Earth reflects roughly 0.3 or 30% of incoming sunlight. Clouds, ice sheets, and oceans together produce this average, though the reflectivity varies widely by surface. Fresh snow can reflect up to 0.9, while deep seawater absorbs most light, creating patches of low albedo across the globe. Astronomers use these values as benchmarks when estimating the brightness of distant worlds. Gas giants like Jupiter and Saturn achieve moderate reflectivity because of their thick cloud decks, composed of ammonia crystals and water vapor that scatter sunlight efficiently. Such atmospheres act like mirrors, preventing heat from escaping too rapidly and lending the planets their familiar pale glow. Against this spectrum, a planet with an albedo below 0.01 sits in radical isolation. It behaves as though its surface, or atmosphere, were designed to consume radiation rather than return it. In physical terms, this makes it indistinguishable from a shadow cast upon space itself. Yet the implications extend beyond astrophysics. Cognitive scientists studying perception often stress that brightness is not absolute, but relational. Ernst Mach, in the 19th century, demonstrated how the brain exaggerates contrasts along boundaries, an effect now known as Mach bands. A planet with negligible reflectivity challenges this mechanism, offering no boundary for contrast to emerge. Seen against the backdrop of its parent star, it risks vanishing into perceptual invisibility. The psychological effect of imagining such darkness parallels experiments in visual deprivation. In the 1960s, John C. Lilly investigated how extended exposure to homogeneous light or darkness altered consciousness. Subjects in flotation tanks reported vivid hallucinations, heightened anxiety, or dissociation from time. Darkness alone acted as a cognitive amplifier, stripping away reference points and leaving the brain to manufacture its own. A planet with near-zero albedo functions as an astronomical counterpart, a body that erases the cues astronomers rely upon to measure, map, and describe. Its invisibility stimulates the same sense of disorientation in thought as sensory deprivation does in perception. Cultural traditions have long attached symbolic meaning to reflectivity. In ancient Chinese philosophy, the interplay of yin and yang often invoked imagery of light and dark, reflective and absorptive, as complementary forces. High albedo surfaces, snow, water, polished metal, carried associations of purity and vitality. Low albedo environments, caves, volcanic ash, moonless nights became metaphors for concealment, transformation, or danger. Anthropologists note that rituals across societies frequently employ low-light conditions to induce altered states. From the sweat lodges of indigenous North America to the catacombs of early Christian mystics, darkness was a medium for reshaping consciousness. When scientists quantify planetary darkness today, they are, perhaps unknowingly, intersecting with a symbolic language that has been cultivated for centuries. In astrophysical practice, measuring albedo requires precise instrumentation. Space telescopes such as Kepler or Hubble cannot directly image most exoplanets. Instead, they detect subtle variations in starlight. When a planet transits its star, a minute fraction of light is blocked. When it passes behind the star, astronomers compare the star's brightness with and without the planet's contribution. If the difference is imperceptible, the inference is that the planet reflects almost no light. The margin of error in these measurements is razor-thin, requiring statistical models and repeated observations. Yet, the consistency of results across multiple telescopes confirms that some exoplanets genuinely exist in this near-invisible category. The broader implications of these measurements resonate in both scientific and psychological domains. For planetary scientists, albedo is a clue about atmospheric composition, surface chemistry, and thermal dynamics. For cognitive scientists, it becomes a metaphor for the limits of detection, how minds grasp patterns from scarce data, how absence itself acquires meaning. The interplay between astrophysics and psychology converges here, each field pushing against the edge of perception. One outward into the cosmos, the other inward into the architecture of the brain. As researchers continue to refine these techniques, the notion of albedo extends into realms far beyond academic journals. It reshapes the way we imagine unseen worlds, how we describe the texture of absence, and how we respond to the disquiet of objects that refuse to shine. The darker the measurement, the greater the tension it imposes, leaving open questions about what kinds of matter, chemistry, and forces could sustain such defiance of light. That tension persists, unresolved, like a shadow stretching further than expected.
The identification of trace 2b came not through direct imaging, but through a convergence of observation and inference. In 2011, NASA's Kepler mission delivered data precise enough to reveal patterns hidden within faint fluctuations of starlight. The parent star of trace 2b, a G-type star located roughly 750 light-years away in the constellation Draco, produced periodic dips in brightness every 2.47 days. Each dip represented a transit, the brief interval during which the planet crossed between star and telescope, blocking a small portion of stellar light. By mapping the regularity of these transits, astronomers established the planet's orbit, mass, and size with extraordinary precision. From the beginning, trace 2b appeared anomalous. Gas giants of its class, so-called hot Jupiters, typically exhibit reflective atmospheres laden with clouds of silicate particles or ammonia crystals. Yet in the case of trace 2b, no such brightening occurred. Even accounting for observational noise, the reflected light from this world was nearly non-existent. The planet absorbed nearly all illumination from its host star, reducing its albedo to less than 0.01. To appreciate the extremity of this figure, one must remember that even a lump of charcoal, placed under a lamp, reflects more photons back into the eye than this gas giant does across the span of interstellar distance. The strangeness of trace 2b resides not only in its physical qualities, but in what those qualities demand of human perception. A star is visible across unimaginable gulfs because it radiates. A planet, by contrast, is revealed only in the traces it leaves: a flicker, a dimming, a wobble in the gravitational balance of its host. When that planet refuses to return light, its existence becomes a study in absence. The brain must construct reality from subtraction, engaging neural processes similar to those activated during perceptual illusions. Experiments in cognitive neuroscience, such as those by Vilayana Ramachandran on negative afterimages, demonstrate how the visual system conjures impressions from missing data. Observing a planet like Trace 2b requires the same leap, to interpret darkness not as emptiness but as substance. The discovery was not an isolated triumph, but part of a lineage of human attempts to map the invisible. Just as William Herschel in the late 18th century detected infrared radiation beyond the visible spectrum, or Wilhelm Röntgen uncovered X-rays hidden from ordinary sight, the Kepler mission extended perception beyond what the retina alone could ever apprehend. Each breakthrough required tools that outstripped the limitations of the body, yet each still returned to the same cognitive threshold: the uneasy blending of absence and presence. In this sense, Trace 2b sits alongside these earlier revelations as an object that alters not only scientific models but also the boundaries of perception itself. The psychological resonance of such a discovery cannot be overstated. In studies of attention, researchers such as Daniel Kahneman have shown how the human mind prioritizes anomalies, events that deviate from pattern, whether a missing beat in a rhythm or a black planet orbiting a bright star, command disproportionate focus. This attentional bias once served survival, drawing awareness to threats or opportunities. Applied to astronomy, it explains why the darkest planet captivates imagination. It embodies deviation on a cosmic scale, a violation of expectation that refuses to resolve into familiarity. Equally striking is the cultural dimension. Across mythologies, the black sun, the shadowed world, or the invisible land often stood for thresholds between ordinary existence and hidden domains. In alchemical texts, the stage of Nigredo, the blackening, symbolized dissolution, the necessary descent into obscurity before transformation. The discovery of a literal blackened world in the heavens intertwines with these symbolic patterns, not by intention but by resonance. It is as if the cosmos, indifferent to myth, has nonetheless delivered an image that confirms archetypes embedded deep within human thought. From a technical standpoint, Trace 2b is remarkable for its orbit. Hugging its star at a distance of only 5 million kilometers, far closer than Mercury lies to our Sun, it endures tidal forces and stellar radiation at intensities that strip conventional assumptions away. Such proximity locks the planet into synchronous rotation, one hemisphere eternally facing its star while the other remains in perpetual night. On the day side, the atmospheric temperatures soar beyond 1000 degrees Celsius, creating conditions hostile to reflective clouds. The night side, though cooler, is still inhospitable, a realm where any light that dares enter is devoured before it can scatter back into space. Astronomers analyzing the data encountered a puzzle that transcended technical curiosity. If clouds were absent, what chemical processes accounted for the extraordinary darkness? Theories pointed toward gaseous sodium, potassium, or titanium oxide, substances capable of absorbing large swaths of visible light. Yet confirmation required deeper probing, spectroscopy at resolutions not yet achieved at the time. The absence of data became its own form of presence, a lingering uncertainty that continued to drive inquiry. The more researchers looked, the more they realized that the planet offered almost nothing back, only faint, elusive signatures, like whispers behind a locked door. What stands out in the psychology of this investigation is the persistence of attention in the face of minimal stimulus. Experiments in signal detection theory show how the mind grapples with faint signals, balancing between hits and false alarms. In the search for exoplanets, astronomers confront the same dilemma. How to distinguish true worlds from statistical noise. With trace 2b, the darkness itself became the signal. Unlike other detections, which depend on brightness curves and reflective contrasts, this world announced itself through absence. The paradox sharpened scientific focus while simultaneously unsettling perception, for it suggested that vast bodies could orbit stars almost undetected, hidden in plain sight. The existence of such a planet forces a reorientation of both astronomy and psychology. It underscores how knowledge often arises not from what is observed, but from what refuses to be observed. The tension between presence and absence becomes the engine of discovery, pushing inquiry deeper into both the mechanics of matter and the architecture of perception. And in the case of Trace 2b, that tension has not diminished but continues to expand, drawing researchers into questions that remain unanswered, suspended like a shadow stretching across the stellar horizon. Trace 2b is frequently described in stark comparative terms: darker than asphalt, darker than the deepest coal seam, darker even than acrylic paint engineered for minimal reflectivity. To quantify such darkness is to confront the limits of language, for human cognition relies heavily on visual metaphor. Asphalt shines under streetlights, coal glitters faintly when struck by sunlight, even the night sky scatters starlight and airglow. Trace 2b offers none of these cues. Its measured reflectivity of less than 1% reduces it to a planetary phantom, present in orbit but absent in vision. If it were transported into the solar system and placed beside Jupiter, the contrast would be disquieting. Where Jupiter's swirling bands of white and ochre reflect like a storm-laden lantern, Trace 2b would appear as a void, a cutout silhouette that refuses to participate in illumination. The mechanics of detection depend not on visible light, but on the faint glow of thermal emission. Objects too hot to remain inert radiate in the infrared, releasing photons invisible to the human eye but detectable by telescopes equipped with sensitive instrumentation. Trace 2b, at a surface temperature exceeding 1,000 degrees Celsius, smolders with a dim redness of heated iron. From Earth, that glow reaches us as a whisper across 750 light-years, a signal so faint it would vanish without the careful filtering of instruments designed for precisely this purpose. To describe the planet as glowing like embers is both accurate and misleading. Accurate because its infrared output matches that of hot coals. Misleading because no human eye could witness it unaided. The paradox of a dark yet glowing planet resonates with principles of cognitive psychology. Perception operates through contrasts, and contradictions exert a unique pull on attention. Studies by Leon Festinger in the 1950s gave rise to the concept of cognitive dissonance, the mental discomfort created when conflicting information resists reconciliation. A planet invisible in visible light, yet radiant in heat, embodies this contradiction, producing a tension not merely scientific but psychological. The mind attempts to unify opposites: light without brightness, visibility without reflection, and in doing so becomes more captivated by the anomaly. From a chemical perspective, the explanation for such low albedo lies in absorption. The gases that compose the atmosphere, sodium, potassium, and possibly titanium oxide, intercept photons across a broad range of the visible spectrum. Instead of scattering light outward, as water droplets or ice crystals would, these atoms and molecules capture energy, transferring it into thermal motion. In laboratory conditions, spectroscopy demonstrates how each element possesses unique absorption lines, narrow windows where incoming light is swallowed. When multiplied across a thick planetary atmosphere, these effects overlap until scarcely any light escapes. What remains is not transparency but an engulfing opacity, a sheath of absorption that transforms starlight into heat. The consequences for planetary climate are severe. Without reflective clouds to deflect stellar radiation, the atmosphere heats to extremes, creating turbulence and violent winds. On Earth, albedo functions as a stabilizer. Ice reflects sunlight, moderating temperature. Clouds scatter radiation, buffering surface heat. Remove these feedbacks, and a planet enters a feedback loop of heating, a self-reinforcing cycle that deepens its hostility. In this respect, TRACE 2b provides an astronomical laboratory for studying the fragility of equilibrium. Climate scientists, though focused primarily on terrestrial systems, have drawn indirect lessons from such exoplanets. The principle is universal. Alter the balance between reflection and absorption, and conditions shift rapidly into states beyond habitability. The study of extreme darkness also intersects with human symbolic frameworks. Darkness has long been associated with concealment, transformation, or annihilation. In medieval cosmology, Dante imagined the pit of hell as a place where no light reached, a realm of smothering shadow. In Mesoamerican myth, the journey through Xibalba required traversing houses of total darkness, tests of endurance that stripped initiates of sensory stability. Such traditions resonate with what is now observed scientifically. The most alien worlds are not those illuminated in spectacular colors, but those that defy sight itself. The absence of light becomes the defining characteristic, a feature that demands not passive acceptance but active interpretation. For neuroscientists, this provides an opportunity to reflect on the role of absence in cognition. Experiments on sensory illusions repeatedly show how the brain fills gaps with constructed content. In the Ganzfeld effect, subjects exposed to featureless fields of light or darkness often report hallucinations, the mind inventing patterns where none exist. TRACE 2b becomes a cosmic-scale version of the same principle, a featureless body that forces observers to rely on instruments and inference, while the imagination supplies images of what cannot be seen. The tension between measurable data and imagined experience creates a fertile ground where science and psychology converge. Yet even with careful measurement, uncertainties persist. The albedo of TRACE 2b is not precisely zero, but its value remains so close to the limit of detection that questions linger about variability. Could storms briefly form reflective clouds, only to dissolve in heat? Could chemical processes fluctuate with altitude, producing transient glimmers invisible to current instruments? Astronomers debate these possibilities, while engineers design future telescopes to resolve them. Each unanswered question sustains the enigma, extending inquiry into deeper layers of planetary physics. The more TRACE 2b is studied, the more its paradoxes multiply. It glows without shining, absorbs without limit, orbits visibly yet hides from the eye. Each property strains conventional categories, leaving observers suspended between certainty and doubt. The planet refuses to stabilize into an ordinary example, keeping inquiry active, attention sharpened, and imagination unsettled. And in that refusal, it hints that other worlds may exist under conditions even stranger, waiting to reveal themselves not through brilliance, but through the overwhelming gravity of their darkness. The depth of TRACE 2b's darkness cannot be explained by distance or size alone. It demands an examination of its atmospheric chemistry. In planetary science, the atmosphere serves as both a filter and a canvas. Photons arriving from the star interact with molecules and aerosols suspended in gaseous layers, and the outcome of those interactions determines whether light is reflected, transmitted, or absorbed. On Earth, nitrogen and oxygen scatter blue wavelengths, while clouds composed of condensed water droplets return vast amounts of light back into space. On Jupiter, ammonia crystals produce its pale reflective bands, and methane filters shape the deeper tones of Uranus and Neptune. Yet on TRACE 2b, these familiar processes fail. Spectroscopic studies indicate the presence of alkali metals, such as sodium and potassium, in gaseous form. Both are notorious absorbers of visible light, each displaying broad resonance lines that capture large fractions of the spectrum. Laboratory experiments on sodium vapor lamps, used for decades in street lighting, demonstrate this principle on a small scale. The lamps emit a narrow yellow glow precisely because sodium atoms absorb and re-emit that specific wavelength. When expanded into an atmosphere thousands of kilometers deep, The absorption becomes so dominant that incoming starlight disappears into thermal energy rather than scattering outward. Compounding this effect are molecules of titanium oxide and vanadium oxide, species capable of intercepting not just narrow bands but broad continua of light. In cooler atmospheres, such compounds might condense into reflective clouds, but at the extreme temperatures of trace 2b they remain vaporized, creating a dense optical screen. The result is an environment that behaves less like a mirror and more like a sponge, soaking up illumination and leaving almost no reflection for distant observers to capture. For cognitive scientists, the significance of this lies not only in chemistry but in perception. Human beings tend to imagine planetary atmospheres in analogy to terrestrial skies: clear blue days, cloudy overcasts, fiery sunsets. When faced with an atmosphere that absorbs rather than reflects, the mind falters, for there is no visual metaphor grounded in experience. Instead, one must conceptualize a sky that denies light itself, an inversion of expectation that generates unease. Psychological experiments on expectation violation, such as those conducted by Jerome Bruner in the mid-20th century, demonstrate how strongly the brain resists anomalies. Subjects presented with playing cards altered to violate standard suits, for example, a red spade, often fail to recognize the error at first glance. In a parallel way, a planet that refuses to reflect light defies recognition, forcing scientists to question the reliability of instinctive interpretation. The role of heat intensifies this effect. Trace 2b's close orbit ensures temperatures that prevent the condensation of bright clouds. On Jupiter, thick ammonia clouds dominate the upper atmosphere, scattering sunlight back into space. On Trace 2b, those potential reflectors are destroyed by heat before they can form, leaving only absorptive gases. The absence of clouds removes the possibility of reflective brightening, cementing the planet's identity as a world of engulfing opacity. The physics of heat drives chemistry into states unfamiliar to terrestrial experience, and chemistry in turn dictates the psychology of how such a world is imagined. The analogy to altered states of consciousness becomes compelling here. Just as heat alters atmospheric equilibrium, disrupting reflective stability, extreme conditions in the human body disrupt the balance of neurotransmission, producing altered perceptions of reality. Hypothermia, for example, can induce hallucinations, confusion, and loss of orientation, phenomena rooted in the destabilization of neural function. Similarly, the atmospheric hypothermia of Trace 2b destabilizes the normal expectations of planetary optics, leading to perceptions that unsettle because they refuse categorization. Both cases illustrate how systems under stress reveal unanticipated states, whether in neurons or in gas giants. Cross-cultural traditions often identify darkness with transformative fire, a paradox mirrored by Trace 2b's profile, a body that glows with heat yet refuses to shine. In Hindu cosmology, the goddess Kali embodies both destructive flame and consuming darkness, a union of opposites that terrifies and fascinates. Alchemical texts refer to the calcinatio, a stage of burning that strips matter of impurity yet leaves only black residue. Such imagery resonates uncannily with a planet whose atmosphere is both furnace and shroud, radiating heat while devouring light. These parallels do not imply mysticism in astronomy, but reveal how deeply symbolic frameworks align with empirical anomalies. The deeper question concerns variability. Astronomers continue to ask whether Trace 2b's atmosphere might shift dynamically, producing transient reflective events masked by current resolution limits. Planetary weather systems are notoriously volatile. On Neptune, for instance, storms larger than Earth form and dissipate within years, altering albedo significantly. If similar but faster phenomena occur on Trace 2b, then its extreme darkness may be punctuated by brief flashes of brightness. Detecting such variability would require instruments capable of sustained, high-precision monitoring, capabilities that are only now being approached with next-generation telescopes. The pursuit of these measurements reflects a broader theme in cognitive science: the mind's struggle with intermittency. Humans are adept at identifying stable patterns, but less comfortable with phenomena that appear sporadically. Inattention blindness, documented in studies by Arian Mack and Irvin Rock, demonstrates how transient signals often go unnoticed if they violate expectation. A planet that glimmers only in rare atmospheric shifts risks evading detection, not because instruments fail but because attention falters. The possibility that trace 2b harbors fleeting moments of reflectivity keeps inquiry alive, an unresolved condition demanding vigilance. The chemistry of this atmosphere, the violence of its heat, and the cognitive dissonance it produces together shape an image not of a stable darkness but of a dynamic abyss. Each advance in measurement strips away assumptions while exposing deeper contradictions. Instead of closure, investigation generates new uncertainty, suggesting that the planet's blackness is not an endpoint but an evolving state, a frontier that continues to absorb attention as completely as it absorbs light. The orbit of trace 2b places it in a category astronomers describe as tidally locked. This condition arises when the gravitational pull of the parent star exerts a continuous torque on the planet's rotation until one hemisphere becomes permanently oriented toward the star, while the opposite hemisphere remains in perpetual darkness. The same principle governs the relationship between Earth and its moon, ensuring that only one lunar face is visible from our vantage point. On trace 2b, however, the consequences are magnified by proximity. At merely a few million kilometers from its host star, tidal forces are immense, leading to a synchronization that fixes day and night into absolute permanence. The day side of the planet is exposed to relentless stellar radiation. Temperatures rise to levels exceeding molten rock on Earth, producing a furnace-like environment where gases churn with violence and particles are stripped of electrons in ionizing cascades. On the night side, the absence of direct irradiation reduces temperatures considerably, though not to levels that would allow stability. The contrast between hemispheres creates extraordinary pressure gradients, driving atmospheric circulation of unparalleled intensity. Winds may surge at thousands of kilometers per hour, carrying heat and material across hemispheres in turbulent, supersonic streams. Such conditions alter not only the physical state of matter, but the conceptual categories through which humans approach the idea of climate. On Earth, the alternation of day and night provides rhythm, a temporal framework that structures biology and psychology alike. Circadian rhythms, governed by the suprachiasmatic nucleus in the human hypothalamus, rely on light-dark cycles to synchronize hormonal release, sleep, and alertness. In the absence of alternation, as in environments of unbroken day or night, those rhythms destabilize. Experiments conducted in the mid-20th century, such as Michel Sifry's subterranean isolation studies, showed how human time perception disintegrates without external light cues. On trace 2b, the very fabric of planetary time has no alternation, only stasis, an unyielding day and an unyielding night. The psychological implications of such constancy, though speculative, speak to the disorientation produced by environments that deny rhythm. The physics of tidally locked planets also reveals patterns of instability. On Earth, the redistribution of heat depends on ocean currents, atmospheric jet streams, and seasonal shifts. On trace 2b, heat transport relies almost entirely on atmospheric flows between hemispheres. These currents create a complex balance. Too little transfer, and the day side overheats catastrophically. Too much, and the night side becomes destabilized by excess energy. Models of such systems show oscillations and chaotic eddies, conditions that could lead to the formation of high-altitude jets and vortices large enough to rival the dimensions of continents on Earth. The violence of such weather exceeds terrestrial comprehension, existing in a regime where atmospheric physics pushes against the limits of fluid dynamics. The study of this imbalance connects directly with human psychology through the notion of homeostasis. Claude Bernard and later Walter Cannon described homeostasis as the equilibrium that organisms must maintain to survive. Just as the human body regulates temperature, pH, and glucose, so too do planetary atmospheres regulate energy flows. When systems deviate too far from balance, pathology emerges in biology and instability in planets. The darkness of trace 2b is inseparable from this imbalance. Its absence of reflective clouds removes a stabilizing mechanism, forcing the system into extremes where oscillation replaces equilibrium. From a cultural standpoint, the concept of eternal day and eternal night has long served as metaphor for extremes of consciousness. In Norse mythology, the realm of Muspelheim burns with unending fire, while Niflheim remains shrouded in endless cold. Each embodies not moderation but absolutes, landscapes without transition. The human psyche, encountering such extremes, projects onto them states of permanence, obsessions, compulsions, or fixations that resist change. The planet becomes an external analogue of internal conditions where balance is lost and continuity replaces alternation. The challenge for astronomers lies in observing such conditions across immense distances. Direct imaging of trace 2b remains beyond current capacity. Instead, evidence arises from the fine analysis of transit light curves and the subtle shift in spectra as the planet moves across phases. By examining the heat signature when the planet disappears behind its star, scientists infer the distribution of energy between hemispheres. These measurements require not only precise instruments, but also algorithms capable of disentangling noise from signal. Every photon captured by a detector carries both meaning and ambiguity, demanding a decision about whether it belongs to the planet, the star, or random fluctuation. The cognitive load here mirrors that of perceptual psychology, where ambiguous figures can be interpreted in multiple ways depending on context and expectation. Researchers pursuing these signals confront the problem of partial evidence. The curves and spectra reveal fragments, yet the whole remains concealed. This condition recalls the Gestalt principle of closure, where the mind completes incomplete forms. A circle drawn with gaps is still perceived as a circle. In studying trace 2b, astronomers engage in an act of closure on a cosmic scale, inferring atmospheric dynamics and orbital behavior from partial, flickering traces. The risk, as always, lies in completing the picture inaccurately, in imposing coherence where the system itself may be unstable. As instruments improve, the prospect of mapping the atmospheric flows of trace 2b becomes more tangible. The James Webb Space Telescope, with its infrared sensitivity, has already begun refining the contours of such worlds. Early observations hint at day-night contrasts sharper than predicted, raising questions about whether current models underestimate the ferocity of the winds or the absorptive depth of the gases. The discrepancy between prediction and measurement acts as a pressure point for inquiry, urging reconsideration of both the physical models and the psychological assumptions that frame interpretation. Every refinement uncovers new tension. The more detail emerges about this world, the less stable its image becomes. Certainty recedes, replaced by recognition of how little light, literal or conceptual, escapes from it. This darkness continues to draw attention not simply because it is measurable, but because it resists assimilation into the frameworks that usually domesticate astronomical discovery. It remains as a disturbance at the edge of comprehension, pressing against the instruments that detect it and the minds that attempt to imagine what such a place must be. The peculiarities of trace 2b extend into its gravitational relationship with its star. Close proximity generates not only tidal locking but also tidal heating, a process by which the planet's internal structure is stressed by gravitational gradients. On Earth's moon, tidal forces have smoothed terrain and influenced volcanic history. On Jupiter's moon Io, they ignite volcanism so extreme that lava fountains rise hundreds of kilometers high. On a gas giant like trace 2b, the effects differ, for the interior is composed not of solid rock but of compressed hydrogen and helium. Yet gravitational flexing still stirs the deep layers, enhancing atmospheric turbulence and perhaps contributing to the redistribution of absorbed stellar energy. The constant deformation of such a body introduces a dimension of instability. In fluid dynamics, oscillations within a pressurized medium can generate resonances, amplifying movements far beyond their initial scale. Applied to a planet's atmosphere, this principle suggests the possibility of standing waves, patterns of motion that persist as semi-permanent features. These might manifest as colossal jet streams locked to the substellar point, or as vortices swirling endlessly in the terminator zone, the twilight band separating the scorched day side from the engulfing night. The scale of such structures would dwarf terrestrial analogues, their dimensions stretching across thousands of kilometers, their persistence rivaling geological epochs. For cognitive researchers, the concept of resonance evokes another layer of interpretation. The brain itself operates on oscillatory principles, with neuronal assemblies producing rhythmic patterns detectable as brainwaves. When resonance is disrupted, whether by neurological illness, sensory deprivation, or induced states of trance, the perception of time, self, and environment alters dramatically. To contemplate a planet whose very body is shaped by oscillations is to confront a parallel between the physics of worlds and the neurodynamics of consciousness. Both systems reveal the capacity of resonance to reshape stability into turbulence, and turbulence into patterns not easily predicted. The intensity of irradiation from the host star compounds this turbulence. At such close orbital distances, stellar winds bombard the planet with streams of charged particles, stripping lighter elements from the upper atmosphere. Observations suggest that many hot Jupiters develop comet-like tails of gas trailing behind them, invisible in ordinary light but detectable in ultraviolet spectra. If Trace 2b shares this trait, it would exist not as a perfectly bounded sphere but as a body shedding matter into space, its atmosphere continuously eroded while its orbit holds it fast. The image is one of endurance under assault, a world forced into perpetual attrition, yet retaining coherence through gravitational grip. Culturally, images of erosion under relentless force resonate with metaphors of psychological wear. Just as individuals exposed to unremitting stress show cognitive and emotional depletion, planets subjected to unceasing stellar winds display forms of loss. In psychology, this is described as allostatic load, the cumulative cost of maintaining stability under pressure. On a planetary scale, Trace 2b embodies an astronomical allostatic load, its atmosphere bearing the consequences of unending stress, its structure adjusting through processes invisible yet consequential. The observational challenge lies in measuring these erosive outflows. Instruments must isolate faint ultraviolet signatures from stellar backgrounds, a task complicated by the variability of the host star itself. Stellar activity introduces noise, flares, spots, and oscillations that mimic or obscure planetary signals. To disentangle these requires statistical rigor and patience, echoing the demands placed on human perception when filtering signal from noise in everyday environments. Just as attention can be overwhelmed by distraction, instruments too can be deceived by stellar variability, requiring layers of correction before planetary truth emerges. Emerging technologies promise refinement. Space telescopes designed with higher spectral resolution and improved noise suppression may capture the delicate fingerprints of atmospheric escape. Such data would illuminate not only the scale of loss but the chemical composition of the escaping gases, offering insight into the deep chemistry that sustains the planet's darkness. Each incremental improvement carries the potential to overturn assumptions, revealing conditions stranger than models predicted. In this sense, the planet acts as a crucible for methodology, forcing innovation in detection just as much as in theory. The interplay between erosion and endurance sustains tension. If atmospheric escape proceeds unchecked, questions arise about the long-term stability of such a world. Yet the very existence of Trace 2b suggests resilience. It has persisted long enough to be detected, orbiting stably despite hostile conditions. The juxtaposition of fragility and persistence mirrors themes central to both biology and psychology, where organisms endure stress through adaptation, even as the cost of that endurance accumulates. The same duality appears on a planetary scale, where destruction and survival coexist in unresolved balance. The more closely Trace 2b is examined, the more it resists simplification. Its darkness is not an isolated trait but part of an interconnected system shaped by resonance, irradiation, erosion, and instability. Each factor contributes to an atmosphere that remains difficult to capture in models, a system whose very elusiveness guarantees its hold on attention. And as instruments refine and theories expand, the expectation persists that deeper layers of contradiction and anomaly remain hidden, waiting to emerge as the next frontier of uncertainty. The study of Trace 2b also raises profound questions about measurement itself. To detect a planet that absorbs nearly all incoming light requires methods that reach beyond ordinary observational intuition. Astronomers rely on the transit method, where a planet passing in front of its star reduces the star's apparent brightness by a fraction. In the case of Trace 2b, the dip is so slight that it demands comparison to the most delicate measurements in science, rivaling the precision required to detect gravitational waves or to measure subatomic oscillations in particle physics. The instruments must register changes in brightness less than a few parts per 10,000, separating planetary signal from the background noise of stellar variability and instrumental fluctuation. The very act of distinguishing such a signal illustrates a broader theme in cognitive science: the ability of the human mind to extract meaningful patterns from noise. Visual perception studies show how the brain detects edges, contours, and motion in environments filled with competing stimuli. Experiments by David Marr and later computational neuroscientists revealed that the visual cortex operates by constructing representations from sparse input, filling gaps and inferring structure. In this sense, astronomers mirror neural processes, transforming fragmentary light curves into coherent planetary models. Yet where the brain often errs by creating illusions, scientific instruments are constrained by physical laws. Their interpretations can be corrected, though always under the pressure of ambiguity. Once the presence of Trace 2b was established, attention turned to the secondary eclipse, the moment when the planet slips behind its star and its emitted radiation vanishes from view. By measuring the difference in infrared flux during this event, scientists inferred the thermal glow of the planet itself. This approach is not intuitive, for it relies on subtraction, learning about a body not by what it reveals, but by what disappears when it is hidden. The method recalls psychological techniques in which absence reveals presence, such as in projective tests where omissions or silences disclose as much as statements. The planet, by vanishing briefly from the star's radiation, disclosed its own faint glow. The philosophical implications of studying an object defined by its near-total absence of light resonate with traditions of negative space in art and culture. In Japanese aesthetics, the concept of ma refers to the interval or emptiness that shapes perception, the silence between notes or the void within architecture. In Western painting, chiaroscuro emphasizes form by contrasting deep shadow with illumination. Trace 2b extends these principles into astrophysics, where its identity emerges not from brightness but from shadow, not from reflection but from the stubbornness of absorption. It represents a celestial embodiment of negative space, a presence constructed by absence. The challenge of representation extends beyond science into psychology. Human beings are ill-equipped to imagine true blackness. Even in the darkest terrestrial environments, caves sealed from light, deep-sea abysses, polar nights, some form of reflection remains. Photons scatter, faint bioluminescence flickers, or residual starlight seeps through the atmosphere. Absolute darkness is alien to perception, producing effects that disorient. Subjects in sensory deprivation chambers often report that blackness itself becomes unstable, filled with imagined flashes or drifting patterns. The mind resists void, imposing invention where input fails. Applied to trace 2b, this suggests that human imagination may never fully capture its condition. The brain will substitute texture, gleam, or storm where none may exist. The implications for exoplanetary science are profound. Traditional categories, rocky, gaseous, icy, rest on properties that can be observed or modeled with some degree of familiarity. A planet like Trace 2b, whose defining characteristic is the refusal of light, unsettles these categories. It occupies a conceptual margin, a body identified not by what it shows but by what it withholds. Such anomalies expand the taxonomy of planets, compelling new frameworks that accommodate worlds resistant to vision. The epistemological tension here intersects with broader studies of uncertainty. In decision theory, uncertainty is divided into risk, where probabilities can be assigned, and ambiguity, where probabilities themselves are unknown. Trace 2b belongs to the latter category. Its properties are not merely difficult to measure, but challenge the very models that would predict them. Each new observation introduces as much ambiguity as it resolves, keeping the system suspended in a state of open inquiry. The phenomenon exemplifies how science advances not only by solving problems, but by generating questions that resist premature closure. Technological progress promises to deepen rather than resolve this uncertainty. With higher resolution, astronomers may detect subtle asymmetries in the planet's brightness across its orbit, signals of atmospheric circulation or chemical variation. Yet each new dataset risks revealing contradictions, a brightness fluctuation too faint for current models, or a spectral feature inconsistent with expected chemistry. The pattern mirrors the trajectory of psychological research, where increased resolution of measurement often exposes variability previously hidden, expanding the field of unknowns. The persistence of darkness as both a physical and symbolic property ensures that Trace 2b will continue to unsettle. Its absence of reflection contradicts instinctive expectations about how worlds should appear, and its dependence on indirect detection forces scientists to adopt methods of inference rather than direct vision. In this sense, it functions as both astronomical object and psychological experiment, probing not only the boundaries of planetary science but the limits of cognition itself. Each new attempt to capture its essence promises not clarification but deeper entanglement, sustaining the tension between what is measured and what cannot yet be imagined. The problem of Trace 2b reaches deeper when examined through the lens of thermal balance. Unlike reflective worlds, which shed incoming energy back into space, this planet absorbs nearly all incident radiation. The absorbed energy must go somewhere. It cannot vanish. Infrared observations reveal that the planet glows faintly with heat, radiating in wavelengths invisible to the human eye. Its darkness in the visible spectrum is therefore not a lack of energy, but a translation of energy into a domain inaccessible without specialized instruments. What emerges is a paradoxical identity, invisible to sight, yet radiant in spectra beyond natural perception. Such a paradox resonates with the human nervous system, where signals can bypass conscious awareness yet shape behavior. Subliminal perception studies in the mid-20th century demonstrated that stimuli below conscious thresholds still influence decision-making and emotional responses. The case of Trace 2b operates as a planetary analog. It emits strongly, yet its emissions fall outside the range of vision, producing a body that is simultaneously active and concealed. The encounter with such phenomena illustrates the limits of human faculties, reminding us that the categories of bright and dark, visible and invisible, are conditioned by biology rather than absolute in nature. The radiative properties of the planet also raise questions of structure. If the atmosphere absorbs visible light with high efficiency, what physical processes prevent it from simply overheating until reflective mechanisms emerge? The answer lies in the physics of radiation equilibrium. The planet continuously converts stellar energy into thermal emission, establishing a dynamic balance between absorption and re-emission. Yet because emission occurs at longer wavelengths, the visible spectrum remains suppressed, reinforcing the impression of unrelenting blackness. In this sense, the planet exemplifies how systems can maintain equilibrium not by moderation but by transformation, redirecting energy into channels inaccessible to ordinary vision. This transformation has psychological analogues. Stress research demonstrates how individuals under unremitting strain may adapt not by reducing stressors but by shifting the mode of expression, redirecting energy into symptoms, rituals, or alternative behaviors. The system appears balanced outwardly, though internally it operates in unfamiliar registers. Trace 2b functions comparably, sustaining balance through a redistribution that conceals the violence of its energy intake beneath a cloak of darkness. The stability is genuine, yet it reveals itself only in forms alien to direct intuition. On the astrophysical front, the absence of visible light complicates mapping. Traditional albedo calculations rely on reflected sunlight, yet here reflection is negligible. Instead, astronomers turn to phase curve analysis. By monitoring how the planet's emitted infrared light waxes and wanes across its orbit, they reconstruct patterns of heat distribution. These patterns suggest currents that transport energy from the day side to the night side, though imperfectly, leaving gradients sharper than models anticipated. The failure of models to align precisely with observation underscores the limits of existing atmospheric theory when applied to extreme regimes. The gaps in theory carry significance beyond astronomy. They parallel the uncertainties that emerge when psychology confronts phenomena resistant to measurement. States of altered consciousness, for example, where self-report is unreliable and physiological markers are ambiguous. In both domains, inquiry must proceed with partial evidence, constructing frameworks that remain provisional, ready to be overturned. The difficulty is not an impediment but a condition of progress, keeping research alive through the pressure of unresolved contradiction. The cultural imagination has long treated heat and darkness as contradictory forces. Fire illuminates, casting light even as it destroys. Darkness conceals, extinguishing fire's visibility. Yet Trace 2b fuses the two, a world aflame yet hidden, radiating energy while refusing light. This fusion recalls symbolic traditions that identified the underworld as both burning and black. Dante's Inferno, Zoroastrian hells, or the volcanic chasms of Polynesian myth. Such parallels do not equate science with myth, but reveal how human cultures have long grappled with the unsettling union of heat and darkness, anticipating through metaphor what astronomy now encounters as reality. As instruments refine, there arises the possibility of detecting spectral signatures beyond heat alone. Molecules leave fingerprints in the way they absorb and emit radiation, producing lines that betray their identity. If future telescopes capture these, the chemical architecture of Trace 2b may come into sharper focus. Yet the expectation is not reassurance but further strangeness. Gases existing at temperatures where chemistry itself approaches dissolution, compounds persisting in regimes where intuition predicts instability. Each discovery promises to disrupt established boundaries, suggesting that the catalogue of possible planetary chemistries remains vastly incomplete. The persistence of such gaps guarantees tension. Every attempt to define the planet collapses into paradox: dark yet radiant, stable yet eroded, concealed yet detectable. Rather than resolving these contradictions, observation multiplies them, expanding the field of uncertainty. The effect on the scientific imagination is comparable to that of optical illusions on perception. The closer one looks, the less stable the image becomes. The object appears to retreat into ambiguity just as evidence accumulates. The pursuit does not clarify so much as intensify, carrying inquiry further into zones where knowledge must remain provisional. The trajectory of this investigation suggests that what is most disquieting about Trace 2b is not its darkness alone, but the way that darkness continues to absorb explanation as completely as it absorbs light. Each new approach, spectral, thermal, chemical, symbolic, dissolves into incompleteness, leaving the planet suspended as an unresolved presence. And as methods advance, the prospect remains that the very act of seeing more will expose only deeper layers of what refuses to be seen. The strangeness of trace 2b extends into the realm of orbital mechanics. Its position relative to the host star is so intimate that questions arise about long-term stability. Gravitational tides act not only to synchronize rotation, but also to alter the orbit itself. Over astronomical timescales, energy dissipation may cause gradual inward migration, pulling the planet closer toward the stellar surface. If such a drift is occurring, trace 2b occupies a transitional state, secure in its orbit for now, yet always under the influence of forces that could lead to engulfment. The delicate balance evokes comparisons to precarious systems in physics where equilibrium persists not by robustness, but by ongoing adjustment. Theories of orbital decay gain weight when considered alongside stellar evolution. As stars age, their luminosity and radius shift, altering the radiation environments of surrounding planets. A world like Trace 2b, already trapped in a narrow orbit, would be exceptionally vulnerable to such changes. Even minor increases in stellar output could accelerate atmospheric erosion, driving mass loss at rates sufficient to reshape the planet's bulk composition. The possibility that Trace 2b may not always exist in its current form raises questions about planetary identity itself. Is a planet defined by its present characteristics, or by the processes that continually reshape it? The issue of shifting identity links directly to cognitive and cultural frameworks. Human beings construct identity through continuity, yet neuroscience demonstrates how plastic the brain is, reorganizing itself after injury, adapting to new sensory inputs, or reshaping under prolonged environmental changes. A planet subjected to unrelenting alteration embodies this same principle on a cosmic scale. It endures by changing, and the cost of that endurance may be the loss of any stable definition. In contemplating such transformations, science touches not only on astrophysical mechanics, but also on philosophical questions about persistence and change. The orbital neighborhood of Trace 2b is also worth scrutiny. Hot Jupiters often exist without close companions, perhaps because their migration disrupts or ejects other bodies. If Trace 2b followed a similar trajectory, it may have destroyed or scattered smaller worlds during its inward spiral. This destructive migration leaves an invisible signature, a system shaped by absence rather than presence. In planetary dynamics, the silence of missing neighbors speaks as loudly as the detection of existing ones. The idea that a single giant body can alter the fate of an entire system resonates with historical analogies, where dominant powers reshape landscapes not only through direct presence, but also through the erasure of alternatives. Detection of such scars in orbital architecture relies on indirect evidence. Perturbations in the star's wobble, irregularities in transit timing, or gravitational signatures too faint to observe directly. These methods demand inference from fragments, a mode of reasoning shared with psychoanalysis, archaeology, and historical reconstruction. Each discipline works with traces, building narratives from what remains rather than from what is directly observed. Trace 2b becomes an object of science in the same manner, a palimpsest of forces, detectable only through shadows, absences, and deviations. The question of habitability, though irrelevant in the literal sense for such a furnace, nonetheless arises in broader context. Exoplanetary science thrives on comparative logic. To know why Earth sustains life, one must also study why countless others do not. The inhospitable darkness of Trace 2b sharpens contrast, highlighting the fragility of the narrow band in which life can persist. Just as pathology reveals the workings of health, so too do hostile worlds illuminate the delicate conditions under which biology can thrive. The study of extreme darkness and heat is not diversionary but essential, revealing boundaries that circumscribe the possible. From a neurological standpoint, the contemplation of such extremes triggers cognitive stretching. humans evolved to imagine landscapes of Earth-like scale, governed by cycles of light and dark. Worlds of perpetual blackness and unbroken heat resist this imagination, forcing reliance on abstract reasoning rather than embodied intuition. In experiments on mental imagery, subjects struggle to visualize impossible colors or four-dimensional objects. The difficulty lies not in lack of intelligence, but in the architecture of perception, which encodes assumptions shaped by survival on Earth. To grasp trace 2b, then, is to confront the limits of cognition itself, recognizing that understanding may consist less in visualization and more in mathematical description. This tension between mathematics and imagination has long shaped scientific revolutions. Non-Euclidean geometry preceded the acceptance of curved space, and quantum theory demanded acceptance of probabilities over certainties. Trace 2b adds to this lineage, demanding recognition of worlds that contradict perceptual instinct. Its darkness is not merely a curiosity but a training ground for thought, pressing cognition to expand beyond familiar categories. Each measurement becomes both a data point and a psychological exercise, requiring the scientist to inhabit perspectives where absence defines reality. Future prospects hinge on technology yet to be deployed. Interferometric arrays in space may one day resolve hot Jupiters directly, separating their light from the blinding glare of host stars. If applied to trace 2b, such instruments could reveal spatial maps of emission, showing weather systems in real time across its hemispheres. But the very ambition of such projects underscores the scale of difficulty. It requires not only engineering advances, but also conceptual frameworks ready to interpret what such unprecedented images might reveal. The risk is that new clarity will not simplify but complicate, exposing turbulence too chaotic for stable models, or chemistries that defy conventional thermodynamics. The expectation of further contradiction sustains the drive of inquiry. Darkness here is not absence but provocation, an ongoing demand for explanation. The closer scientists come to resolving its mysteries, the more layers of resistance they encounter. And as technology reaches toward direct confrontation with this world, the anticipation grows that what emerges may unsettle not only astronomy, but also the human frameworks through which reality is made intelligible.